Okay, so now we're going to do another practice one since we kind of had to stop that one. We were getting close to 30 minutes on that. So what we're going to do here, we're going to do another practice one here. We're going to look at what we were just doing with determining the acid dissociation constant Ka with given an initial concentration of our acid and then a pH at equilibrium. So when a 0.5 molar solution of hydrofluoric acid is prepared, the pH is found to be 2.34 at 25 degrees C. What is the acid dissociation constant Ka? So remember, the first thing we always do is Ka is equal to H plus 1 times F minus 1 all over HF. Okay? And then we're going to plug our initial values into our ice table. So we're going to have 0.50. And then because it hasn't done any dissociation at this point, we're going to be at 0 for both of these. Now, according to Le Chatelier's principle, if we're putting in some type of concentration on our reactants, it's going to move over to our products. So it's going to be minus some concentration here, and we're going to add some concentrations over here. Now, I'm not going to fill in my equilibrium concentration because remember, what do I need to do? Find my equilibrium concentration for my hydrogen ions. Okay? So this we're going to find from the pH. So we go pH is equal to the negative log of the hydrogen ion, concentration of the hydrogen ion. Okay? So our pH was 2.34 is going to equal negative log of our hydrogen ion concentration. And remember, did some math, but we found that if we do take our hydrogen ion concentration, it's going to equal 10 to the negative 2.34. You remember how we did that in the last video. So we put that into our calculator and we get our hydrogen ion concentration. And it should be kind of close to the last example we just did. So remember, second, 10 to the negative 2.34. Okay? So I'm going to get 0.00457. Okay, and that's going to be molar, my concentration. So I can go ahead and put that back into my table here. Remember, because whatever I have for my hydrogen ion concentration is going to be my X. So my equilibrium concentration for my HF is going to be that minus X. Okay? So if I want to go ahead and determine my concentration of HF, it's going to be 0.50 minus X. So if I substitute in this concentration here for X, it's going to be 0.50 minus 0.00457. Okay? So again, just to prove my point here, this is going to be my number that I'm going to get for my hydrofluoric acid concentration. And if I round that number, I'm going to get pretty much the same thing I just had. So this is what I'm going to put into my Ka equation. Does that make sense? So if I plug that number in, using my concentration that I found for my hydrogen ion or my fluoride ion, okay, I'm just going to put that into my calculator. Round that off to one decimal place. We're going to get 4.2 times 10 to the negative 5th. Okay? So, this should be a little bit easier than what we were doing the last time, because remember, we couldn't just say that it was negligible difference. Now we can. So it makes it a lot easier to find that. But what if we're given the acid dissociation constant and instead told, hey, let's find the pH? So how do I do that? Well, first step, what do you think that's going to be? It's going to be the same thing that we've done over and over and over and over and over again. We're going to first start by writing the acid dissociation constant equation. Okay. And when we're calculating for this pH, it's going to be very similar to what we did to calculate for the concentration at equilibrium for those problems that we did in the last unit. So the same thing, we're going to follow similar steps here. First is going to be to make an ice table. Okay. So I'm going to do that for you in these packets, but if you're ever given this on a test, you need to make your own ice table. Okay? And remember, ice is initial, change, equilibrium. So the next step, plug in all values into the ice table. Okay? And that means this time too, we're going to put in, instead of trying to find, we already know what our concentration is for hydrogen, for our hydrogen ion. Instead, this time we're going to go ahead and put in X for those. We're going to see that in a minute. So, we're going to use our acid dissociation constant equation. We're going to plug in the given Ka and the formulas that we came up with for the equilibrium concentrations which we have in our ice table. So remember, these come from our ice table. Now, here's where things get a little bit easier than in the last unit. The last unit, we couldn't assume something. Remember, I told you, you don't really need to change what the initial concentration is of your acid because the difference is negligible, right? It's super small. So we were just going ahead and ignoring it. Here, we can assume the same thing. So we're going to assume that X is negligible. And that's because, remember, our hydrogen ion concentration is always going to be small enough that it doesn't matter. Okay, remember, that's why we write it as a pH. Okay? And we're going to remove this from the reactants portion of the acid dissociation constant equation. Because remember, we start out with a concentration that's large enough that the difference between the concentration that we're going to have at equilibrium and the concentration we start with is negligible. So therefore, we just use the concentration that we started with. Similar situation here. Then, once we've gone ahead and solved for X, okay, once we've solved for X, we're going to go ahead then using X as our hydrogen ion concentration. We're going to find the pH. Okay, so we're going to go ahead and go through an example of this. So here we're using acetic acid, and this is found a lot of times within vinegar. Kind of common. So, it does not smell very good, FYI. So, when a 0.30 molar solution of acetic acid is prepared, the acid dissociation constant is found to be 1.8 times 10 to the negative fifth. What is the pH of this solution? So remember, what's the first thing we always do? We're going to write our equilibrium constant equation, or in this case, our acid dissociation constant equation. So to do that, I'm going to put my hydrogen ion concentration, with my acetate ion all over my acetic acid concentration. The next step is to make my ice table and then plug in my values to my ice table. So I start off with 3.0 molar, right? Here I've got nothing. Here I've got nothing. So remember, if I'm going to be putting, according to Le Chatelier's principle, if I'm putting in reactants, equilibrium is going to shift to the right. It's going to shift towards the products. So therefore, I'm going to have minus x here, plus x, and plus x. So my equilibrium concentration should be 0.30 minus x, and then we have 2 x's. Okay, so this next part's going to look a little similar to what we just did in this previous unit. First thing we're going to do, we're going to find it. We need to solve for x here, right? So we need to write our equilibrium or acid dissociation constant equation again. Okay, so what we're going to do is we're going to plug in our given Ka, and then we're going to plug in what we find in our ice table. Remember, these two were both x's, and then 0.030 minus x. Okay, so we're going to assume that x is negligible, and by assuming that, we're going to have x squared over 0.30. We're going to make this go away. Make that disappear. Okay? So then all I got to do is take x squared is equal to, I'm going to multiply by 0.30 on both sides. So that should give me 1.8 times 10 to the negative 5th times 0.30. Okay? And then if I take the square root of that number, I'm going to go ahead and first solve for that. Okay, if I take the second square root of that in order to get rid of my x squared, I should get 2.3 times 10 to the negative 3. Okay? So, again, remember we're going to assume that x is equal to the hydrogen ion concentration. So therefore, my hydrogen ion concentration should equal 2.3 times 10 to the negative 3 molar. Okay? And then the last step, we're going to use this number to find our pH. So pH is equal to the negative log of our hydrogen ion concentration. So pH is equal to the negative log of 2.3 times 10 to the negative 3. So if I do that, if I put in my negative log 2.3 times 10 to the negative 3, get 2.6, and that's my pH. So does this seem a little bit easier than the previous problem, the previous chapter that we did, where we had much more difficulties because of the fact that we could not assume that x was negligible? Because we already know that whatever our hydrogen ion concentration is going to be very small. We can assume that x will be negligible and therefore eliminate it compared to this larger concentration that we started with. Does this make sense? Okay, let's do one more example of solving for the pH. Okay, going backwards. So here, when a 2.0 molar solution of hydrogen cyanide is prepared, the acid dissociation constant is found to be 4.9 times 10 to the 10th. What is the pH of this solution? Okay. So just like we do with the rest of these, we always start with the same thing. Okay, and that's writing our acid dissociation constant equation. Okay. So, First thing we're going to do, write Ka is equal to our hydrogen ions times our cyanide ion all over hydrogen cyanide, which is technically an acid. It follows kind of the same principles as an acid because it does break apart to give you a hydrogen ion. Okay? So, we started off with a 0.20 solution, and here we have nothing. 0 and 0. Now remember, according to Le Chatelier's principle, if I put something in here, I'm going to move to the right. So therefore, I'm going to subtract out x, add x, and add x. So here I should get 0.20 minus x. We have x and x. Okay, so now I've filled in my ice table. So now my next step is to go ahead and plug that back in to my acid dissociation constant equation. So if I write that out, Ka is equal to H plus 1 and then the times the concentration of the cyanide ion all over HCN, or hydrogen cyanide, whatever the concentration is for that. So my Ka was 4.9 times 10 to the negative 10th. Okay, I'm going to multiply the x times x all over 0.20 minus x. And see, that should match up with what I have here, and then the initial acid dissociation constant that I've been given. Okay, so now I can assume that x is negligible. Remember, I can assume that it's small. So therefore, I should get x squared all over 2.0. Get rid of that x. Okay? Then I multiply on both sides by 0.20. Get x squared is equal to that number. Okay? And then if we take the square root of that, we should get x is equal to that number. So let's go ahead and do that in our calculator. Oh, I should say x is equal to some number, which we're going to solve for right now. Okay, so I have that when I multiplied that out. I'm going to go ahead. Okay, so I'll round to 1 decimal place here. 9.9 times 10 to the negative 6. Okay, now if we assume that x is going to equal my hydrogen ion concentration, then my hydrogen ion concentration should equal 9.9 times 10 to the negative 6 molar. And then the final step for this whole process is to put the pH is equal to the negative log of our hydrogen ion concentration. So our pH is going to equal negative log of 9.9 times 10 to the negative 6. So if I put that in, negative log 9.9 second e to the negative 6. This is what I get. Round to 1 decimal place. I should get 5.0 as my pH. Okay. So hopefully this is actually a lot easier than what we were doing in the last chapter. And if you mastered the last chapters, last unit stuff, this will be pretty easy for you, okay? I've kind of blended a couple of chapters together with this unit too, so you'll notice that in your homework as well. Okay. So, now we're done with the acid dissociation constant, at least for the moment. The next one we're going to talk about is the base dissociation constant. And it's very similar to what the acid dissociation constant is. Okay? So this is going to be the equilibrium constant for the ionization of a weak base in water. Again, this is always will contain a base reacting with water to form what you're going to find out is we call a conjugate acid. Acid, which for our purposes will be anything that has the plus 1 ion. Okay. And OH, so a hydroxide ion. Okay. So here's what our typical base equation should look like. Some type of base with our water goes to form our conjugate acid, a B with whatever has a plus 1 charge, and our hydroxide ion. Now, what is the one thing that I can eliminate when I'm writing my base dissociation constant equation? I can eliminate my liquid. So I don't have to write my water in there. Because remember, if I have any solids or liquids, they're not included in any equilibrium constant equation that I write. I only include aqueuses and gases. So the same thing applies to a base dissociation constant because it's just the equilibrium constant for a weak base. Okay? So I'm going to write this as my products over my reactant. Okay? And that's how I write my KB. So I'm going to stop the video right here. We're going to go ahead in the next video looking at solving for KB, knowing either the pH or the pOH. Okay?